Okay. Lab turned in. Make sure you're getting that turned in. Make sure you have the POGL turned in if you weren't here. Do you have that, Maggie?
Yeah.
Excellent.
Yes. We did just do the other lab yesterday, so it was very cool for that to be due today.
What'd you say? For the lab?
Yeah.
Calculations. Oh, the RFs. I'm grading the
question.
I'm grading the questions.
There's not that.
All right. Today I'm answering questions on the homework. Tomorrow we're playing a review game. Friday we're doing the AP classroom portion of the test, which is, I told you there's a lot, right?
No.
Was there like 16 questions or something I said? I think there's like 16. I don't even know what the schedule looks like Friday. I just know it's short periods. So we might have some extra time just to hang out too. Cool? Okay. Question number what are we starting on?
Whoa.
Anybody has something lower than 83?
Literally one.
Yeah.
Number one.
Literally one.
Number one says, is it possible to bounce a paper clip on the surface of water in a beaker? It is possible. If you add soap, paper clip sinks. First of all, why can it float?
Surface tension.
Is it adhesion or cohesion?
Surface tension.
Okay, surface tension. Okay.
Or also known as adhesion.
It floats due to surface tension from what?
We guess the hydrogen bonds.
Hydrogen bonding. So I don't want you guys just to say surface tension. I want you to say hydrogen bonding. Okay? Then I put soap in there and it sinks.
Does the soap interfere with the hydrogen?
How? It sinks because soap has a polar and a non-polar end.
Are you just supposed to know this?
You would have had to have Googled that. I don't know how you would have known that. But soap has a polar and a non-polar end, and that's how soap cleans. So if it runs into something polar, right, then the non-polar end attracts it and it takes it away. If it runs into something non-polar, it takes it away. Soap cleans oil from oil's non-polar, right?
Yeah.
So the polar end of soap will then bring that oil away. So it sinks because soap has a polar and a non-polar end. So the hydrogen bonds are dipole, right? Yes?
Yeah.
So the polar end of soap will repel H bonds, right? Or you could say the other end will attract them. And water molecules spread out. Right? So the polar end will repel H bonds and the water molecules spread out. Or you could say the non-polar end will attract the H bonds and it will spread out. Either way. The soap, if you put soap in, you can actually see soap pushing away. Have you guys ever done where you put like soap in like milk and you put the food coloring in and it like goes blah, 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 like pushes all away? Same thing. Same thing. That's number one. Next one.
3.
2.
Number two.
These weird like explanation ones.
So this is talking about physical equilibrium. There's a difference between physical and chemical equilibrium. We haven't talked about chemical equilibrium. So which one of these did you think best shows physical equilibrium? What'd you guys say? B. Water evaporates until the air is overly saturated with water, and most of this water recondenses. This cycle continues until a certain amount of water vapor is present, and then the cycle ceases. In a water bottle at room temperature, do you see a lot of condensing happening? No, not B. Someone else.
Can I nominate what it's not?
Sure.
It's not E.
I agree that it's not E. Water evaporates until it's eventually all in vapor form. Nope, not going to happen. Okay, so we have 2 gone. Who else has a proposal?
I don't think
Well,
it's,
it does some evaporation.
I don't think it's. I do
So
not
it's
think
not C.
It's not C, okay?
So it's A or B.
It's D.
I had D.
It's D. Water evaporates, right? and then water evaporates and recondenses simultaneously and continuously. That is showing the equilibrium. All right, that's showing the equilibrium. There's always going to be water evaporating. That's the equilibrium. So it's kind of like a process. That's why you're not seeing condensation like it's always going. Yes, so 2 is D.
Wait, so why is it in D?
Huh?
Why is it in?
Why is it not A?
Yeah.
Because the A is saying it will stop.
Okay.
It never stops.
If it's stopping, though,
You might need it. It won't stop. It'll keep going.
if it's stopping, what would that like indicate? I guess what if
Then there's no more water.
That's
The only way it's going to stop is if there's no more water.
real.
That's 2. Next one.
3. Wait, I think I know.
You add 100 milliliters of water to 5. I wish we had time for this. So take a 500 milliliter round bottom flask. I add water to it. I boil it. I cap it right away. Right? Then I pour cold water on the neck. Do you guys know what a round bottom flask looks like? Okay. So what's that going to do to the particles inside? It's going to make them want to slow down. What's that going to do to the pressure inside? Lower pressure inside. Therefore, the particles can more easily escape. That's it. Just gas loss. So as you lower the temperature,
Decrease pressure.
yes, yes, that's
That
it.
makes so much more sense. Whatever I was trying to say.
So number 3, as temperature goes down, we know that pressure goes down. So
You were on drugs.
boiling point also goes down. There's literally less pressure pushing on the surface of the water.
And when you cap it, you don't like take away the heat from the water that was boiling.
Correct.
No, okay, yeah.
Okay, that's 3. Next one.
Hold up.
Okay, 7.
We're just gonna do all these, please.
7. Water is in an open beaker, evaporates over time. As water is evaporating, is the vapor pressure increasing, decreasing, or staying the same? Is the temperature changing?
No.
Stays the same.
Wait, in the notes, that's
It's
not what it
easy,
says.
Jack.
It's like
It's
the step
easy.
piece, right? Yeah, but you said the notes, hold up. Because like in the step
Where did I say in the notes? I said that vapor pressure is directly related to temperature.
I'm just confused.
Vapor pressure is directly related to temperature. I do not think I contradicted myself, but if you find it, let me know.
Yeah, pressure is produced as molecules escape a liquid. The more molecules that can escape, the higher vapor pressure.
Okay.
Water is an open beaker over time, so it's going to evaporate, so molecules are escaping.
But I'm saying, how would you make more molecules escape though?
You'd have to probably boil it.
You have to heat it. Is this temperature of this system changing?
No, but they're still evaporating.
Yeah, but the vapor pressure is not changing. The vapor pressure when there's 100 molecules is the same as the vapor pressure when there's 50 molecules because the temperature is the same.
So like in the notes, this is referring to like any sort of like boiling process.
Correct. So if you said this is true, you were saying that if I have a gallon of water, right, in this bucket, right, you were saying when I get down to half a gallon, it's easier to evaporate. No, it's not. Right?
Yeah.
No matter, it's still water at the same temperature.
So what about surface area like that?
Surface area, it's still gonna be the same surface area too.
Oh, okay.
It's still a bucket, right? So no matter what, if I have a gallon of water or if I have half a gallon of water, unless you change the temperature, the vapor pressure stays the same.
Is it like vapor pressure would then be like a measure of how many are able to escape, not
Yeah.
necessarily the raw kind of molecules that are escaping?
Right.
Okay.
Wait, what if your bucket was like an upside down cone with the big with like the because,
What?
No. Does surface does surface area affect vapor pressure?
Joey,
Yes or no?
No.
No. Okay.
what sort of upside down cone are you going back to?
How do you have an upside down cone? How is that holding water?
It's like a
It doesn't.
you know,
Joey,
you know,
Joey, just let it go.
That doesn't hold water.
Let it go. Joey, let it
no.
go.
You know those paper
Oh,
cups?
dang.
Yeah, you know those paper cups?
I know the paper cups.
Yeah. And they're like little
Number
cups.
8.
Yeah.
You said upside
It holds
down.
water.
You said upside down.
No. But like an upside down cone, as in like you know.
Still, that's not gonna affect it. If it's at the same temperature, it's still gonna evaporate the same amount. Next one. 7 is the same. I did not think I would hear the word upside down cone today, but I did. Next question. 8.
And then we're free.
Water vapor at 100 degrees. What's the vapor pressure? 1.
Be the 1 atmosphere.
Oh,
1 atmosphere. If water's boiling at 100, you have to be at sea level. Has to be 1.
So that means vapor pressure is it impacted by atmosphere?
Yes.
Oh, right, because how many can escape?
Right. You got it. So that's why water in Colorado boils at a lower temperature, because there's less pressure pushing on the outside of that
So
surface.
it's easier for them to escape. So
Correct.
more molecules can escape. So
Yes. Okay? That was the active learning questions.
those.
They're kind of fun. It's good to talk about. The point of those is to talk about them. Next one.
no.
24. Can we just quickly bear with 1 second?
Oh my
It
goodness.
says what role does humidity play?
Okay, so 24, right? So as sweat evaporates from your skin, right? That's cooling your skin. Yes? If it's more humid, it's harder for that water to evaporate. So therefore, it's going to be harder for their sweat to evaporate. That's all that's saying.
That's all it is.
Okay. That was 24.
37.
37. Okay. Let's do 37.
The only thing I don't understand, forget what.
So on 37, here is what I want you to understand. If it is ionic, can it have any other intermolecular force? No. Because that's the only one that is what? Ionic, right? If it is not ionic, it's going to have automatically what? LDF plus maybe something else. Okay?
That's what I need.
So it's going to be ionic, or it's going to be only LDF, right? Or it's going to be LDF plus something else, right? Those are the 3 choices. So it could be LDF plus dipole, could be LDF plus hydrogen bonding, right?
You have hydrogen bonding, but hydrogen bonding is a type of it.
Hydrogen bonding is a type of dipole, but you wouldn't call hydrogen bonding dipole. Okay. So I think it's helpful to know that those are kind of your 3 choices. Okay. So A,
It's just argon.
it's just argon. So therefore, that's just
And just LDF.
LDF. B,
Is hydrochloric acid.
hydrochloric acid.
LDF and
LDF and
dipole.
dipole. LDF and dipole. Letters.
That's really polar, isn't it? HCl.
Yes. Letter C, HF. We know there's LDFs, and then there's also H bonding. Also H bonding. D, ionic. Because remember, is ionic, because this is asking for interparticle forces, is ionic really a type of intermolecular force? No. So once it's ionic, we're out of that area. E, CH4.
It has to have LDF.
There is no dipole there
Isn't the charge evenly?
because here's why. First of all, the charge is evenly distributed. Second of all, if you look at the electronegativity of carbon and hydrogen, it's almost the same. Yeah. So carbon and hydrogen almost have the same electronegativity. But that is London dispersion forces. That is actually considered nonpolar. Nonpolar. Plus CH4, right? Would it be a tetrahedron? F. CO is going to be
LDF.
and
Dipole.
dipole. You got it.
Carbon and oxygen will have they'll have different electronegativities.
Correct. LDF, dipole. And G,
That's ionic.
ionic. Na plus 1, NO3 minus 1.
These are fun. Those are.
Okay. That was 37.
We go over 43.
Yeah, 43.
43.
42.
43.
Basically just the freezing.
42.
So 43 is kind of the same thing, but now we're talking about which one has certain things, right? So 43A, It says which one has the highest boiling point. So I'm looking for the strongest intermolecular forces. Agreed? Okay, so this is going to be HBr. Why?
Dipole and London dispersion.
Right, so this has dipole. I'm just going to write the strongest one, okay? Which is what's making it, because that has dipole.
Well, aren't LDFs like incredibly like small?
Yes.
Okay.
B, which one's going to have the highest freezing point? So once again, I'm looking for, oh wait, no, letter A, HBr, yeah, dipole. Letter B, which one's going to have the highest freezing point? So once again, I'm talking about the strongest.
Why is it high? Why is it strongest in this case? Because it like takes the most to just keep them.
A high freezing point, right, means it freezes at a really high temperature. Think about that, right? It's kind of weird to think about freezing point. It's kind of weird to think about freezing point.
Yeah. Because like low, like a high freezing point is like zero. Like water has a higher freezing point than like something that's below zero.
Yeah, why? Like, why does the strong bonds have to?
Well, water has hydrogen bonding, right? So it freezes at a higher temperature. Freezing point and boiling point are the same thing. That's what you have to think about.
Noted.
It's essentially the same thing explained a different way. Okay. So 43, which one has the strongest NaCl? Why? It's ionic. It's ionic. C, lowest vapor pressure.
That means the least evaporation.
That means the least evaporation. So we're looking for the least intermolecular forces. So which one?
Wouldn't it be strongest thermomolecular?
No, high vapor. Oh wait, so hold on. Lowest vapor pressure would be the strongest. You're right.
So CL2?
Oh wait, oh no, I do. It's
But
the biggest.
I2's bigger. It
More
has
LDF.
more shielding.
But bigger means more LDF.
It's I2 because it has the most London dispersion forces because it's the largest. So these are all LDF, right? But I2 was the largest. So that'd be the explanation for C. D, lowest freezing point. So now
Is it just lowest boiling point?
this would also be lowest boiling point.
So weakest.
So weakest. So D, what's your weakest going to be?
The N2.
Yes, why?
It doesn't. The other two have dipole, and it only has LDF.
N2, you're right. N2 is London dispersion forces. The other two would have, well, hold on.
Wait, no, CO2.
CO2 would not have, but N2 is going to be what compared to CO2?
They're smaller.
It's smaller, right? So N2 is smaller
So that means less LDF.
and less LDFs. E, lowest boiling point.
That's also weakest, isn't it?
Yes, so that's CH4. That's 4, why? Smallest. So that means it has the least amount of LDFs. And then F, highest boiling point?
HF?
HF, why?
Hydrogen bond.
Hydrogen bonding. Yes. HF, because it has H bonding. Am I still on the screen? Yes. And then G, highest boiling point.
Oh, there.
Sorry, lowest vapor pressure.
I mean, that means strongest bonds, yes?
Correct. It means it doesn't want to evaporate.
Well, the last one has a hydrogen bond, so the CH3, CH2, CH2OH has a hydrogen.
That's actually the second to last one. But yes,
Wait,
Is that because the oxygen is double bonded?
it's because it's a hydrogen bond.
Okay.
the OH.
Just because it's a hydrogen bond. That's the only one that has a hydrogen bond in it. That's the second one, right, Megan?
That's the last one.
CH3, CH2OH? Is there not?
That's the third. There's two CH2s. And then
Oh, sorry, I'm on the wrong question. I'm stupid. Yes. So it's going to be CH3, CH2, CH2OH. Because the OH is H bonding.
that singular bond does so much.
It does. That's a lot. So that's 43.
Yeah.
Sure. Why not? So 44. 44 is similar, right?
Yeah.
Yes. So let's make sure we got these right. Make sure we got these right. So 44. Whoops. 44A. This is saying the highest boiling point. So that's going to be the one that has the strongest intermolecular forces, which is going to be what?
CF4.
Why?
No,
CBr4. Why? Largest.
Oh.
So that has the most London dispersion forces. They're all LDFs, right?
Do any of those have like a dipole then?
No. B. Lowest freezing point. So what is that going to be?
F2?
F2. Why?
It only has LAF.
Right. F2
LIF is ionic.
is only LDF, right? We know that LIF is ionic, and then HCl, right, has what?
Dipole.
Dipole. Dipole. C.
It's a dipole.
Smallest vapor pressure. So the one that's going to be the strongest intermolecular forces.
There's a hydrogen bond in the second one.
It's the second one. CH3CH2OH because of H bonding. Because of H bonding. That was C. D. Greatest viscosity, that's going to be the thickest. So that's going to be the strongest intermolecular forces.
H2O2?
Yeah.
It's HS because it's hydrogen.
H2O2 is a hydrogen bond.
H2O2 has 2 hydrogen bonds,
Oh, yeah.
right? HF only has 1.
Does it matter like if the hydrogen bond is between oxygen and hydrogen or nitrogen and oxygen or fluorine?
I mean, it would, but on this one, we're both talking about. Oh no, it shouldn't. It's double the hydrogen bonding is going to be double the power. E.
Greatest heat of vaporization.
Greatest heat of vaporization,
Does that mean most heat required to? That's like the most heat required to vaporize 1 mole.
right?
The strongest form.
So what's that going to be?
H2CO.
H2CO. Why?
Dipole.
H2CO because it is
That's going to be polar.
dipole. It's polar, right? It's polar / dipole. And then F, smallest enthalpy of fusion,
Least energy required.
correct?
I2.
I2, why?
The other two ionic.
It has only LDFs. The other two are ionic. Good. You guys are getting these. Next one.
We just very quickly go over like the answers for 83.
Sure.
Oh, my big thing is what's the difference between I forgot.
83.
Oh yeah, what makes a covalent network? I know it's got to be in group 14, but outside of that, like, what's another criteria you can look for like covalent network?
Doesn't it mostly have 4 things attached to it? Like, isn't that kind of like the big?
I don't know, because what
Silicon
about,
dioxide is a covalent.
Oh, it's also in group 14. But silicon dioxide would have 2 double bonds. Mostly if it's from group 14, that's
hey, but what about CO2? Why is that molecular versus covalent network?
because on that one, carbon dioxide is. Think about that. So carbon dioxide, CO2, that's a solid.
CO2 can be for a little bit
Oh,
more.
these are all solids.
Yeah.
These are all
I
solids.
think it was asking like what sort of solid does it form?
Yes. Let's go through these, and then we'll talk through each one. Let's talk through each one. So 83A. 83A is molecular. You just get CO2 is like a classic. I mean, you just gotta know that CO2 is.
Bro, I hate when people.
It is though. Like CO2 is like the example they gave on the AP classroom for a molecular solid. So that's a molecular.
Oh.
B. SiO2 is
That's gonna be
Covalent network. Yes. C,
Covalent network.
covalent network.
Wait,
How do we know when it's a covalent network?
Group 14.
It's a group 14.
There's 4 attached to it, not always.
So this one
Wait,
on
CO2 is a group.
We've been over this,
We
we've
don't
been
talk
over
about
this.
CO2 is that's a molecular.
It's a classic.
It's a classic. It's a classic.
Okay.
I'll give you a better explanation of why later. D, because I want to make sure we get through all these.
DCH4.
Where are we at? CH4, molecular.
Wait a minute.
Wait
a minute.
No, yeah, this
Why?
is
It's molecular.
CH4 though, but C is in group 14.
carbon spectral.
Obviously.
Well, number, like just carbon.
I think we should just
Covalent.
eliminate covalent network because
That's not gonna work.
I feel like we could just say molecular.
What do you mean?
Jack
Like
wants
I
to make them
don't
all.
really truly understand the difference between the two. Like how do you decide if it's covalent network?
Bless you.
Like for CH4, like the central is going to be the carbon. You have 4 H's attached to it, so why is that not a covalent network? For D.
Where's the notes? Where's the notes? I see.
Covalent network, elements of group 14 can make 4 covalent bonds, and as such allow them to bond together in large continuous networks. Right. Or you say yes.
I feel like that.
Molecular solids. Oh,
It just feels like a,
molecular solids are from 2 nonmetals.
like I could.
But so is silicon dioxide.
Silicon is not a nonmetal.
Wait, silicon?
It's a metalloid. That's how you know. That's how you know.
Wait, restate that again?
Molecular solids are 2 nonmetals.
Where did you find the notes for this?
Right here.
Yeah, but I can't find them.
Here you go.
Here it is.
That's how you know.
Okay.
Good. I'm glad we talked about that.
I am too.
E, rubidium is metallic, because that's a metal.
I'm like, if it's metal.
Exactly. F, I2 is going to be
Molecular.
molecular, because that's technically diatomic, so it's 2 nonmetals of its same thing.
Oh, it's so, oh my god.
G, KBr is ionic. H, I have H2O,
Molecular.
molecular. Now we got it.
There we go.
I have,
Anyways, that's ionic.
that's ionic. F, wait, J, wow, I literally don't know my alphabet. J, U is gonna be metallic. It's a metal.
Okay.
K, thank you for helping me. K,
Ionic.
ionic. And L is
That's molecular.
molecular. Well, that was easy. We good with that now, Jack?
Yep.
Sweet.
Explain that to Danny and Emily, because you're going to have a question.
Well, it's gonna be 2 nonmetals.
Okay.
It's super easy.
93.
93.
You've been wanting to get to this one for
Now we're here eventually.
Oh, it's this. It's the
What is
secret
this?
formula.
Yeah.
Oh, what is so hard about this?
I don't know. I know.
So let's talk about it.
Log, is it natural log?
So 93, Breckenridge, Colorado, atmospheric pressure 520 torr. What's the boiling point of water? 40.7 kilojoules in Breckenridge. So here is how I did this. You need a little bit of an assumption here, right? So I know that the equation is natural log of P1 over P2. So I'm going to write the equation, but it's not hard. Equals delta HVAP over R times 1 over T2 minus 1 over T1. And I'm trying to solve for what?
I think that's
I'm really trying, yes, the question, yes. What I'm going to be solving for here is my boiling point.
Okay, why are we using this equation if only one temperature?
I don't. You're right, because I'm going to solve for X.
Yeah.
I'm subbing for x. I have everything else. I'll show you why. Natural log. What is my pressure?
520.
520 torr.
What's our second pressure though?
Pressure 2 would be,
Oh.
I would do 760,
Two.
right?
Doesn't matter what you.
Why would I do 760?
Sea level.
Because that's sea level, right? Yes.
Doesn't matter which one you use is PVAP 1 and PVAP 2 as long as you keep it.
As long as you keep it consistent. That is equal to, they gave me 40.7, right? But remember, that's going to have to be 40.7 times 10 to the third, right? Joules per mole. So you got to convert that over 8.3145 joules per mole times Kelvin. That whole thing times 1 over, what's my T2 going to be?
Would it be the
Colorado. Wait.
100?
Wait.
Yeah, 100 degrees Celsius. No, that's
Wait.
really not.
Okay, 100 degrees Celsius is what temperature Kelvin?
373.
373 Kelvin
Why did I say Celsius?
minus 1 over T1.
That's
Solve for x.
Look at how. Okay.
So on that one, you just had to assume the other one was your regular.
And you could use like.
Show us how you type in your calculator.
Sure.
actually kind of
I
real.
mean, it's going to be a lot. So I don't care. You can use Desmos. Natural log of 520 divided by 760.
Could you move your calculator a little to the right? So I can
See?
see.
So that gives me a negative. So that means that negative 0.379 equals, now I'm going to do this 40.7, well that's just going to be, I'm just going to change that to 40700, right?
Yeah.
Divided by 8.3145. So that gives me 4895 times 1 over 373 minus 1 over T1. How do you guys want to do this? Simplify more? So negative 0.379 equals 4895 times 1 divided by 373 is 0.00268. 0.00268 minus 1 over T1.
I would have just divided them.
I would have just, yeah.
Yeah, just divide the
And then
4,000.
multiply by 373.
What do you mean multiply them?
The 1 over 373.
What do you mean? Oh, yeah. That would have been a better way to do it. So you divide this over
Yep.
Yeah.
and then just multiply by 373? That would do the same thing.
Because it's
No.
reciprocal.
But there's a subtract there. There's a minus sign. That wouldn't work.
You can multiply.
Oh,
You
yeah,
can still
no,
do it.
that's right.
You can multiply it in half.
No,
Alright,
yeah, but then
can
you would
I
have
don't know.
37. You would have like
Alpha
373
too,
over
I don't remember any of
T1. You
this.
should just subtract. You should subtract the thing. That would work.
Megan, is that
Subtract
a-
where?
Why are you
So
asking me?
1 over
Because if you multiply,
373, can you just flip that?
if you multiply out, if you like divide out the 4895, then you would have 1 over 373 minus 1 over T1. Then you could subtract both sides by 1 over 373. That would make that the answer on the left equals negative 1 over T1. You would get a positive answer. It would be a fraction.
Well, let me keep going this way. Old school. Negative 0.379 equals, I need to multiply those together, 4895 times 0.00268. I'm distributing now. So that equals 13.11 minus 4895 over T1. Yes?
Yes. Yeah.
So now I'm going to, well, don't I need to add this to their side first?
Yes.
So I'm going to add this to their side.
No, the 13 you'll add.
Huh?
You would get T1 by itself.
Wouldn't I add this to both sides? There's lots of ways you can do this.
Yeah, there's just
So I'm going to add,
ways that you can do it.
there's lots of ways. I'm going to add this to both sides. So that's going to give me, I'm showing all my steps, 4895 over T1 minus 0.379 now equals 13.11. Now I'm going to add 0.379.
Oh, I see.
So that gives me 4895 over T1 equals 13.11 plus 0.379. That gives me 13.489. And now I'm going to do what?
I would cross multiply T1 times the 13 divided by
I would cross multiply, right?
489.
So it's going to be 4895 divided by 13.489. So 4895 divided by 13.489. 362 or 363 Kelvin. Yeah, I got 362. So there's 362 Kelvin. Does Desmos make that easier?
You don't even have to solve for it. You can just type it in like the top part and then the graph tells you.
Here's the thing. You would never do something like that on the AP test.
Yeah, bro, where's this one on the AP Chem? It's not.
But you wouldn't do something like this on the AP Chem test.
We better not. I'm curious. Like,
Why? That's too much calculation.
I'm fine with it.
Too much calculation.
One did.
Plus, who wants to grade that?
Not me.
Okay. That was 93.
104.
104?
Yeah.
I'm really proud of my algebra right there, guys. It just made me feel really special.
Algebra is the hardest thing.
That is honestly the most algebra I've done in a long time. But I enjoyed working that out. That was kind of fun. 104. 0.250 chunk of sodium metal is cautiously dropped because it will explode into water. So, 50 grams of water and 50 grams of ice, both at 0. Here's the reaction. Assuming no heat's lost, will ice melt? Assuming this final mixture has a specific heat, calculate the final temperature. The enthalpy of fusion for ice is 6.02 kilojoules per mole. First thing I'm going to do is figure out how much heat am I going to release. So, heat released is going to be, I've got 0.250 grams of Na times Na is still 22.99 grams of Na
Well, they're going to tell us the molar masses are wrong.
and 1 mole of Na. They won't. In this problem, though, how many moles of Na do I have in the balanced equation? For every 2 moles of Na, I get how many kilojoules?
368.
368 kilojoules.
Do you care if we use the positive or negative then?
I don't care. But, because I'm figuring out heat release, so this should technically be positive, the way I wrote it. So that's going to be 2.00 kilojoules of heat released. So now I have to figure out how much heat does it take to melt 50 grams, right? So I have 50.0 grams of H2O times 18.015 grams of H2O and 1 mole of H2O. And 1 mole of H2O, the heat of fusion is 6.02 kilojoules. So I'm going to solve that. So I need, after I solve that, I need 16.7 kilojoules. Will it melt? No. It won't melt. That's 104.
What about the final temperature first?
Oh. Calculate the final temperature. So the final temperature, well, if it doesn't melt, that means there's still ice, right? If there's still ice, the temperature is going to be what? The temperature stays at 0 until the last piece of ice is melted.
Bothers me.
So,
Even though you release heat?
yes. We did that freshman year when we melted ice.
Freshman year.
All right? Remember how we put the ice in the beaker and we melted it? We looked at the thermometer. Temperature did not start going up until the last piece of ice is gone. Because all the energy going in is the amount of energy it takes to break the hydrogen
How
bonds.
fast is the energy, like, how fast does the heat transfer? Because like, would that just be like the heat from, or like the heat from like the surrounding area going into the ice? Because then the ice is melting. I don't know how that works.
The amount of heat going from the hot pad, right?
Yeah.
All that heat is being used to break the hydrogen bonds between the ice particles.
Okay.
So it's equal. So the temperature won't start going up until all of those solid particles are liquid. Then it starts going
How
up.
fast does that happen? Because is there like at a certain point when, I don't know, if you were to like stop time, a certain part would be like have more temperature than the other part?
It's not perfect because eventually your tip of your thermometer is going to be touching water when there's still ice. So,
99 real quick.
sure. 99.
Isn't that just a study?
Yeah, it is.
Oh, snap. If that's a steppy, I'll try.
Wait, all I
Yeah,
need
no,
to know
no.
is it similar to 103?
99.
It's a partial study. It has 4 parts though,
Well, 99. Why is the heat of vaporization larger than the heat of fusion, first of all?
because it takes more energy to
Just takes
completely
more
break
It takes more energy to completely break water molecules apart, right? B, what quantity of heat would be needed to melt 1 gram of sodium?
Would you just do stoic?
On that one, it's melting, so that would just be stoic. But take grams to moles, and then moles to the
2.6.
heat of fusion. C, I would take 1 gram to moles, moles to the heat of vaporization. D, 1 gram of sodium.
Condensed, would that just be the same as C, but like backwards? Because it's
So condensed,
would be
right, that one is just going to be the negative. So on this one, it's just going to be, you would use negative 97 instead of positive 97. And then what was the other one, Jack?
No, that's it.
Do you want the answer for 103 or are you good? You have the answer for 103.
I'm good.
Yeah, we have
Okay.
answers for, I think, all of us.
Cool. Boom. I knew we'd get that in a day.